Okay, yes, let me introduce you, Cesar. Welcome everyone to a new session of our category seminar. Today we have the pleasure and honor of having Cesar Galindo from Universidad de los Andes in Colombia, who will be talking to us about his work on equivariant fusion categories. Before starting, if anyone wishes to ask a question during the talk, please unmute yourself or ask the question in the chat. You don't feel comfortable asking the question in English, please ask it in Spanish. I would be very happy to translate to Cesar. Students are especially encouraged to ask questions. So please, Cesar, thank you, and well, take it away.
Thank you, Carlos, for the invitation. It's a pleasure to be here. Well, I want to talk about our recent work with Corey Jones. And this is related, Carlos tell me about that Julia Plagnik and Eric Rowell talked recently. And this is in some sense quite related, but it's not exactly the same subject, but it's in the same direction. So let me first try I will say more or less what is the idea of the work, and later I will try to give the whole details. The idea basically is the following. There is a notion that I will explain with more details of an action of a group on a tensor category, or in our case of interest is a fusion category. When you have an action of a group on a tensor category, you can define a new one that is called the equivariantization sometimes, or just the category of fixed point. And this is again, let's say, a monoidal category. So a natural question here is, well, can you describe the fusions of categories, maybe in terms of the fusions of categories of your original category and some group theoretical terms? And this is basically our result. It's an answer to these questions and to find some applications of this result. So, so now let me start with some preliminary, and I want to fix, first of all, some notation. So I will denote by G a group, but to be honest, in many cases will be a finite group. But this is not really, for most of the definition, this is not really necessary. And even many of the things can be done for, at least for compact group. But again, here, I will assume most of the time that the group is finite. And the other ingredients that I need, and I will denote by C in general, it's a fusion category. Here, I won't assume that you know exactly what a fusion category is. So I will try to give very quickly, and if there is some, please ask me if something is not clear about this. So what a fusion category is, so the first is that this is a rigid K-linear. So K in general, in my case, even it is not absolutely necessary, just to be safe, I will assume that this K is an algebraic closed field of characteristic 0. Thinking complex numbers, that's good enough. So K-linear abelian category and monoidal. Monoidal, there are many adjectives. Monoidal, K-linear rigid abelian, plus also we need that it must be semi-simple. And the unit object, let's see this, a simple And what else? And and such that there are there is only finite many isomorphism classes of simple objects. All this is a lot, it's very long, but this is the notion of a fusion category. Of course, let's say the archetypical, the typical example, it's the category of finite dimensional linear representations of a finite group. This is our typical example with the usual tensor product. The trivial representation is the unit object, and with the canonical duality, you have a vector a representation. Then the dual is just the ordinary linear dual with the obvious action. And this is the typical example of a fusion category. There are more examples, and later I will present at least one additional example of a fusion category. Okay. So we have, on one hand, we have this group and we have this tensor category. So I want to define what an action of, let's say, of this group G on our fusion category is. So for us, it will be just a monoidal functor. Let me write down G with an underline. I will explain in a second what this means, to this one. And I will also put an underline here. So what is this? So this is the discrete monoidal category. What I mean by discrete, so it is the discrete category where the objects are the elements of the group. So I mean, the objects are just, the set of objects are just the elements in the group, and you only have identities. There is no more than identities. And the product will induce on this category a monoidal structure. This is so you can think of this as a monoidal category. Right? Yeah. And this is again another monoidal category where the objects are tensor autoequivalents and morphisms are tensor natural isomorphism. So what is explicitly here? An action. So an action is something that for every element of your group, you have an associated tensor functor. Here I am omitting some data because when I am saying a tensor functor, it's not just a functor. You also need some natural isomorphism. And so maybe if I want to be, let's say, with more details, it will be something like you have this functor, but also you have some psi, and this psi will be just a natural isomorphism between, this psi will be a natural isomorphism between x tensor y to x tensor y. And of course, the pair has to be a tensor functor. But because I am saying that this is a monoidal functor, in addition to that, you have for every pair of elements, again, a tensor natural isomorphism, let's say, between these two. I don't know, I will call it mu of GH. And this has to satisfy the coherence. So it's some kind of square that has to satisfy, saying that this functor, it's in fact a monoidal functor. Okay. So this is the notion of action. This is an action. You can think in the particular case, let's say, where this is just the identity. If this is just the identity, this looks like a group homomorphism, similar look like a group homomorphism, something that goes from G, let's say, to the tensor automorphism. Well, here I will assume something about the identity to do everything simpler, and it's that the tensor automorphism associated with the identity. In general, I just will assume that there is a monoidal isomorphism to the identity, but here you can prove easily that every, let's say, action is equivalent and another action in such a way that this is equal to the identity as a tensor functor, not just as a functor, but as a tensor functor. So if we add this condition, that it's not restrictive, in fact, and you, for example, assume for a moment that this is the identity, and for example, that also this is the identity, this looks like a group homomorphism from G to the automorphisms of the category. But of course, in nature, it's quite hard in general to find examples where this mu and this psi are only identities. The usual thing that you find, it's something where this mu and this psi are not identities. Yeah, this is the usual thing. Okay, so this is an action of a group on a tensor category. Some people also can call this like an action up to homotopy, or I have find another names for this notion. Okay, so look at, in order to define this, you don't need really that your category C has to be fusion. It's just to be monoidal. That's enough in order to have the definition. And also, the thing is that now I want to define the notion of equivariantization, or the category of fixed point. So the next thing that I need is to define this notion of equivariantization. And so what is the thing? Suppose that you have this group. Look, also, you in the definition of action, you don't need that the group it's finite. In fact, this is defined for every discrete group. But suppose that you have a group that is acting on a tensor category, and now we want to define a new category that will be again monoidal, and I will denote in this way that we will call the equivariantization. So how is this category defined? Let me move this to the next one. So the objects of this category will be just, let's say, will be a pair. When you have an object of your category, so this is an object. And you have also a family of isomorphisms. Indexed by the element of your group. So look, it looks like the object X is fixed under the action, but of course you need some coherent. And here the coherent is just that if you take the action of these two, remember that you have this isomorphism, so you can apply this isomorphism to this one, and then you again can apply the isomorphism, let's say, to this one, and this diagram must commute. In fact, here, to be completely honest, but let me draw the complete picture. Really, here you go to this one, and then you can go to, let's say, here is VGH, and here is G, and here is Q star. Oh, sorry. Yes. This is the diagram that should commute. And here is this that we call here mu. So this is an object in your category. Amorphism, of course, should be something that commutes. So, so for example, if you have X and Y, two equivariant objects, and you have a morphism, I don't know, lambda, and should be the obvious thing, and it's that this diagram should commute, I don't know, for every G. So that it's just a morphism that commute with all the possible actions. So that's define a new category. And but the interesting thing is that this category, in fact, has monoidal structure. And the monoidal structure, look for a moment this category. So what are the objects? The objects are objects in your category plus this morphisms F, and that satisfies some condition. And what are your morphisms? Your morphisms are morphisms is your target category that satisfies an additional condition. So in particular, you have a forgetful functor that takes this and sends just to X. And the monoidal structure is defined in such a way that this forgetful functor is strict. So the thing is, there is a tensor structure on, and this is given exactly by the condition that this functor, this is a strict tensor functor. There is a unique way, in fact, to define this. I won't do the computations, but this is the obvious one. And something interesting is that it looked at the notion of action is given for any possible monoidal category. But something interesting here is, for example, if your category is rigid, then the equivariantization again is rigid. And I don't know, for example, if your category is abelian, and let's say your group is finite, then again, your category is abelian. And even more interesting for us, if our initial category is fusion, it's a fusion category, and G is a finite group, the equivariantization again is a fusion category. So this is a procedure. So the point is, if C is a fusion category, then CG is also fusion. Let me present some examples, at least 2 examples.
Cesar, could I just a quick question? Yeah, for example, when you have a fusion category, I read somehow that it's equivalent that you have that the home of the identity to the identity is just the field. When you have the characteristic of the field is 0 and also at your right most.
Yes.
So why should be this the case for the equivariation of?
Oh yes, I didn't say here what is really the monoidal structure, and also I didn't say what is the unit object. But let me tell you at least what is the unit object. The unit object, it's, remember that an object in your equivariantization is an object in your original category, so it's this one, and you also need a family of natural isomorphism between this and this, and this is the I mean, by definition, G comes with a natural isomorphism in this direction. So is this, I mean, because every G star is a monoidal functor. So by definition, you have a let's say a canonical, or I don't know, an isomorphism from this to this. So this is, I don't know how to call it, UG, let me call it. This is part of the whole structure of your action. And this is the object. And the point is that this object commutes with everything. So when you try to see what are the end of functors of this object, it's again, remember that if your original category was, your original category was fusion. So in particular, this unit object is a simple object. So as you said, the endomorphisms of the identity are just, I don't know, the complex numbers times the identity or the ground field. So the same happened for this. Yeah. And yeah.
And why had this happened for the fusion, the equivariation?
You can think for a moment, just to do things simpler, that your functor it's in such a way that really this happened. I mean, this is not a big deal, because every functor can be replaced for another one that is that has this property. It's just to do the idea, let's say, the computation simpler, but I'm not losing any. So you want to see really what is this. So sorry. So if you have that this is true, then you want to analyze. Okay, if you have that this is true, here you really only need to take really the identity. So these mu are just identity of one. This is this is the way that you see the unit object in the category of equivariant object. It's just the identity plus identity, the unit object plus the identities for every G. So now you want to see what exactly this is. So remember that I said here that morphism is something that makes this diagram commutative. But in your case, this is just an identity. This is just an identity. So, and this is just an identity. And this is, I mean, what I mean is that here, in our particular case, this is one, this is one, this is one, this is one. So it's a, let's say, tautological that the diagram commutes. In the more general case, it follows from some properties of the mu associated with this. But this is basically why this is true in this particular case. So what I'm saying here is that this is, again, this. And we said that this is a one-dimensional. It's a one-dimensional algebra. So that's why this is, again, the unit object is simple.
Okay, yeah.
Okay. Yes. So I want to present two examples. Let me first present the following example. So when you have a finite group, you can associate with this group the category of vector spaces, G-graded vector spaces, and it has a canonical monoidal structure given just by I mean, the simple objects are just these ones. So if you do, let's say that, I mean, are one-dimensional vector spaces graded by the elements of your group. So if you do this is canonically isomorphic to GH. This is the tensor product. So in particular, the unit object is this one, is the one-dimensional vector space graded over the unit object. So the point is that you have that the group G acts canonically on this vector space just by conjugation. Yes. So when you try to see what is, in this case, this one, our intuition said that this is, I mean, if you take, let's say, the group acts by conjugation, and then you take invariance in the case of groups, you get the center. Well, here you obtain the Dreamfield center of the category of vector spaces. Yeah. I don't want to explain here what is exactly this category, but this is a very interesting category that I know that you have seen several times in talk, so I won't want to describe. But there is another version of this. I mean, you can modify using a tricocycle the associativity constraint of your category. And in this case, again, the group G acts on this category. Remember that you need two extra data. You need this, I call in this case, some mu, that is the natural isomorphism that corresponds to this one. And also, I talk about this, I get what it is. Here, when I said action, we have two, the psi, and we also have this mu. So in the case that there is no tricocycle, so the case just of Beck G omega, these are just identities. But in the other case, this is some expression that appears when you that you can deduce from the tricocycle, and these expressions are just related with the translation of the tricocycle. So this is typical data that you obtain in let's say in the construction of the Dijkgraaf-Witten theory. I don't want to explain the details because it takes some time, but the point here is that there is there is some additional data that you can express on psi of G and some mu of GH that you can express in terms of omega, and that gives you the additional information of an action of G on Beck G omega. And the second example that I want to present.
Sorry, Cesar.
Yes.
So omega is just a tricocycle in the homology of the group now.
Yes, yes. Okay. Omega, it's a tricocycle of G with coefficients in K star. Okay. And using this, you can construct some two more functions, let's say some psi and some mu that defines exactly the action. And this is you find the formulas for this, for example, in the paper, the original paper, when the twisted Dreamfield double is defined. Even when let's say in this paper, they don't talk about actions of anything, but it's something well known already.
Right.
Okay, so I think I'm going too slowly. So the other example that I think is quite important is the following. Suppose that again you have your fusion category, and I will assume for a moment that this fusion category, in addition to be fusion, also it's braided. So I will assume that this is braided. And when you take, let's say, the category, suppose that you have again a finite group G, and suppose that you have an inclusion of the category representations of the group G inside of this braided category in such a way that this inclusion is a braided inclusion. So in other words, you have inside of your tensor in your braided category another category that is like a copy of the category representations of a group. Then inside, so always inside of this group, you have a particular algebra. I mean, here in the category representations of your group, this is a monoidal category, even more, it's a symmetric monoidal category. You have inside the algebra of functions over your group. Let me call this A. Okay, just the algebra of functions. And of course, the group has a natural action on this algebra. It's the typical action. And with this action, in fact, this is a commutative algebra inside of the category representations. And because I am assuming that the inclusion of this group inside of B, it's braided, A itself, it's a commutative algebra inside of B. Yeah, because A it's a commutative algebra in the category representations of G. So in this case, you can take the category of A modules in B, because this is again a monoidal category. This is not just a category. You can do tensor product over your category, and this is again a fusion category. I mean, with the tensor product over A, and the unit object is the algebra itself. So this algebra sometimes is called BG, and sometimes it's called de-equivariantization. I won't emphasize, but the point, as I said, is that G acts on the algebra A by algebra automorphisms additionally. So if G acts on A, in particular, G acts on BG, because yeah, you have an action over G, then you can twist your action and you get an action over the whole category. And this is quite interesting. Why? Because on one hand, you have your original B. You can construct a new one that I call B sub G. But you also have an action of your group on this BG, so you can take equivariantization. Well, the interesting thing, and this is an important result, is that those categories are canonical equivalent as a fusion categories, even as a braided categories. They are equivalent as braided categories.
Sorry, Cesar, the last G is the equivariantization or equivariantization? Is
Sorry, there are, yeah, this one sometimes is called equivariantization. So what I am saying is the equivariantization of de-equivariantization, it's equivalent to your original category. Okay. And this is the typical way to see actions of categories. This is a go and back in between two. So in general, if you take, this is something that I didn't say, but in general, in the equivariantization, always there is a copy of the category representations of G. And this corresponds just to all, let's say, all objects supported over the copies of the trivial unit. That's basically what the copy appears. Okay. Now I can say what is the goal of the work. The goal is just to describe all fusion subcategories of CG. That's the goal. So look for a moment that this has interesting applications. One of the interesting applications is that this, for example, allow us to describe the fusion subcategories of the twisted Drinfeld double. And this is a very interesting result. In fact, this was done previously, like 10 years ago, by Naidu, Nikic, and Witherspoon. And this is in some sense the motivation for our paper was to generalize this construction, not just to the case of the twisted Drinfeld double, but in particular to all possible action of a group on a fusion or even a monoidal category. Okay, so again, this is the goal. The goal, describe all fusions of category of the equivariantization. Let me try to I will directly try to give the statement of the main result of the paper, and later I will try to give some applications. So the main result is the following. fusion subcategories of the equivariantization are parameterized by triplets where first, this is a fusion subcategory of C, but more, it's a G invariant fusion subcategory. And I know that I haven't said what a fusion subcategory is. So this is something that I will do in a moment. This is something that I haven't said. Second, age. This is the other parameter. This is just a normal subgroup. And third, this thing is a G invariant. Trivialization of the H action on E. And again here, I know that I haven't said what I mean by trivialization and even what I mean by G invariant. So let's first, I want to say what is a G invariant fusion subcategory. So here, remember, for every element of your group, you have a tensor autoequivalence of C. And now we have a fusion subcategory. So that means just that for every element of your group, the image of this is again inside of E. So it is stable under the action of your group. That is just that. So look that in particular, G restrict to a new action on the category E. Okay, so that's the first. Now the second, I will just say what is a trivialization. Still not G invariant, it's just what is a trivialization. So remember, I said a trivialization of H. That's important. I mean here, yeah. So, but in general, remember that here we have that the action of G restricts to an action of E. So we have, as I said, an action. So what means an action? Again, this is by definition a tensor functor from H seen as a monoidal category to the tensor automorphisms. And here I have my action that just came from restriction to the original action of G over C. And also, we always have here the trivial action. What means a trivial action? The trivial action is just to every element of your group H, you are associated the identity of E. And for every pair of elements, you are associated the identity. So it's this is the trivial action. Everything is the identity. A trivialization, this eta that I described there, is just a monoidal natural isomorphism from the action to the trivial action. That is a trivialization. This is by definition a trivialization. So what exactly that means? That means that for every element, I mean, you have this G and you have this X and you have a natural. I mean, what I'm saying is that we have an isomorphism that I will denote, let's say, in this way. And this is that has to satisfy. I mean, I am saying that this is a tensor natural isomorphism. So it has to satisfy some coherence. Yeah, but this is just a trivialization. And now I need to describe what means this to be G invariant. Look that at this moment I haven't used at all that H is normal. I mean, this is not important. So to talk about this G invariant here, I really need that H is normal. So to be G invariant means basically the following. You have your G. Here H is an element in the normal subgroup, and G is just an arbitrary element in your big group G. So what I'm saying here is, okay, you have this, and now you can apply, remember that we have this trivialization, so we can apply this. And we apply this, we have this. This is part of the data. But here I want to use that H is a normal subgroup. So you have that this thing. Look here. This is an element again in H. And using the natural isomorphism of the action, there is a canonical isomorphism from this part to this part. And now I can apply here again and the idea is that this diagram commutes. That's the notion of G invariant trivialization. Okay. So now I explain what are the data. And I want to describe quickly how to go from one of these, let's say from this data to a fusion subcategory and vice versa, very quickly. And if the time is enough, at least to present a simple example. Okay, so first, let's say what happens if you go from one of these triple to a fusion subcategory of the equivariantization. This is let's say the first thing that I would like to describe. Okay. So remember what a trivialization is. A trivialization is a natural isomorphism from the action to the trivial action. So this trivialization allows us to give a description and to define an inclusion of the category E over the objects of the equivariantization over H. This is given just using the trivialization. So the trivialization, it's give us a procedure to define an inclusion of the functor there. Maybe I should, well, okay. And now the other thing is that remember that H is a normal subgroup, so the quotient is a group, and the point is that this acts on the category of invariant objects respect to the H. This is something typically. And now the G invariant condition. I mean, this is all we always have, that the quotient acts on CH, but the G variant conditions implies, and in fact is equivalent, implies that this inclusion, I mean, that this, it's a GH invariant. What I mean is GH acts on this, and we have this inclusion. So, okay, yeah, this is so how I construct D. So D is just, now that I know that this, I have this, I take the equivariantization. This is include inside of this, but this is canonical equivalent to the equivariantization. That's the way that I construct D inside of the equivariantization of G. This is the whole procedure. And how to go in the other direction. In the other direction is if I want to go from, let's say, a fusion subcategory to this one, Then the idea is the following. Remember that we have a forgetful functor. And by definition, I have this. So my E will be just the, let's say, the image of D, that is a category inside of C. And now the normal subgroup, it's defined by the conditions that, remember that the tensor subcategories of the category representation of a group are in correspondence with normal subgroup. So this is in such a way that this is the intersection between rep G and our original D. And yeah, and the additional data, this eta, came basically because we proved that in fact the action can be, it's trivializable. This is a technical point that I don't want to discuss here with much more details, but we proved that in fact the action on this of H over this E, it's can be trivialized, so you need to pick one, and this is more or less the way. That, of course, the typical application, I mean, there are some applications. The typical application that we develop in our paper is you can pick, let's say, I will change the words. Suppose that K is a finite group and you have the category of K vector spaces with a 3 cocycle, then you pick an action. Let's say that the twisted Dirichlet double corresponds to the case that K is equal to G and you're acting by conjugation, but in particular, you can take any possible action. And then we describe here what are the fusion subcategories of the equivariantization. And this is interesting because some some semi-simple Hopf algebras came from this construction. So that gives us a way to describe or parameterize Hopf subalgebras of some family of Hopf subalgebras that are the Hopf algebras that are called Katz-Palutsky algebras. But I think I should stop here. Yeah. Thank you.
Okay, thank you very much, Cesar. I think you stop in the best part. Is there any question for the audience? I don't know if you could, Cesar, you could give you an idea of what are the fusion subcategories of the equivariantization of vector. That is the Dirichlet double. No?
Oh, of the Dirichlet double. Yes. Yes. Yeah, let me try to explain very quickly, even a little more general. Mm-hmm. So you have a group acting on this category. What kind of data means to have an action of your group on this kind of category? That means first to have just an action by group automorphisms on this group K. So this is part of the data. In our case, it's just act by conjugation. And the other part of the data is to have, in this case, two more additional. One is some beta that depends of G, K, and L. And it's a family. And the other data is this mu of GH K, again here. K, it's an element in K, and G and H are elements in G. So you can look, for example, of this data as an element, I don't know, in C2 of, let's say, K with coefficients in C1 of G. This is another way to see. And this mu, you can see as an element in C of G with coefficients in, let's say, K. It's two ways to see this. And you have some conditions like, I don't want to enter in, but some is that, let's say the mu is a 2 cocycle and some relations between omega that you can describe. But my point is that these additional data that you need in order to describe are, let's say, parameters of this way. So when you try to see what are the, let me see where it is. This thing, in our case, C is Beck G. So what are the fusion subcategories of Beck G? They correspond just to subgroups. It's just that subgroup of H. And the thing that is G invariant means that the group has to be invariant under the action of the other group. Yes, this is part of the data. And later in the second, we need a normal subgroup, so just as a normal subgroup. And then in the third part, we need a trivialization. A trivialization means that the elements of, the action of the normal subgroup on these others, there are many subgroups, sorry. But in the subgroup associated with the category E, the action should be just the identity. So when you act, it's exactly the identity. So when you translate, for example, what all these conditions to the case of the group G acting over itself, it'll tell you that the categories are in correspondence with pairs of subgroups, one commuting with the other, plus some cohomological data that satisfies some funny equations. But this funny equation has cohomological interpretation. So in fact, even you can, let's say, compute obstructions to the existence of these functions.
Oh.
But all the details are in the paper of Dimitri, Naidu, and Witherspoon, and with this generalization in our paper.
Okay. Yep. Well, and there is another question by Juan. Juan?
Yes. Yeah. Hi, Cesar. Thank you very much for the talk. I'm sorry I was a bit late, but well, one just first very basic. So just one very basic question is, so you mentioned equivariance, equivariantization preserves fusion. Does it preserve the condition of being spherical? So is the equivariantization of a spherical fusion category still is again spherical?
Well, if the action is given by a spherical monoidal functors or for pivotal functors, yes. Yeah. This is easy to see that this is the case. But if it's not, there is not a clear way to provide to the equivariantization of a spherical structure.
Okay. So I suppose the general is like, should we think of this things that equivariantization preserve as, if your action is good enough, preserves your structure, then the equivariantization preserves that structure. So is that the case with braided and modular and everything?
Well, modular, no. Modular is very tricky. But for braided, this is a good example. I mean, you can have many tensor functors, and only some of them are braided.
Yeah.
And if you pick just an arbitrary functor and take the equivariantization, again, this is a fusion category and there is no problem. But there is no an obvious way to define again a braided structure. So you
but if the action is braided, then you get a braid. You can
yeah, but what is,
reconstruct it.
yeah, exactly. But what is the important part? The center, what people some people call the what is the name? Some people call the Muger center, or another people call the transparent objects. Always the copy of the representations lives inside of the transparent objects. So you can start with a modular category, but when you take parentization, this is not modular anymore.
Okay.
There is another procedure called gauging that is different, but that this procedure allows you to go from modular to modular, but it's more complicated.
Okay. Yeah. Thank you. Well, so suppose you're in a spherical fusion category and you act spherically, then you take the equivariantization, it's again spherical.
Yes.
What happens to the Tura-Viro invariant? Do you get something new, interesting?
I don't know.
Okay.
I don't know. Yeah.
Okay.
To be honest, I don't know if there is a directly description of one in terms of the other. No.
Okay.
Yeah.
Yeah, that's interesting. Thank you. Well, another question. So Julia's talk was really interesting and lots of fun. But they seem so Sesting and equivariantization seem like are defining terms of sort of this homological sort of or I don't know, co-cycle data or something, but somehow unrelated. But is there a relation between Sesting and equivariantization?
I have also that question.
Oh, I mean, philosophically talking, they are related, but directly I cannot. I can tell you what is the relation, but there is no an obvious relation at this moment for me. The relation is the following. Basically, an action, as I said, it's a group homomorphism from, a monoidal functor from here to here. This is basically an action.
Yeah.
And assessing, it's something similar. No, it's not something similar. It's something more complicated. No, I cannot see the relation. Yeah. And I don't know if there is a relation now.
Okay. Okay. Yeah, somehow it seems like the tensor functor of the action would be some sort of somehow like there's co-cycles everywhere, but I suppose in fusion categories there's always co-cycles everywhere. So I mean that doesn't say anything. But yeah, okay. Thank you.
Thank you.
Yeah, so I'm sorry. I don't want to ask too many questions, but just another question. So in the de-equivariantization procedure, you mentioned that you needed your category that you want to de-equivariantize to be braided. Why? So do you need that to define the algebra, or why do you need it? Why do you need that?
Yeah, that's an excellent question. Thank you. I mean, because in many of these cases, the equivariantization doesn't have a canonical braided action. So we said that there are something. Well, the reason is the following. You always can. I mean, supposing in general that you have a fusion, an arbitrary tensor category, and you have inside a group G.
Yeah.
So as I said, here inside you have the algebra A. So there is no any problem to define A modules over C. However, there is a big complication with this, is that there is no a canonical monoidal structure over this, because in general, the thing that has a canonical monoidal structure, it's A bimodals. A bimodals always has a canonical monoidal structure, because this is but in the case that your category is braided, and your inclusion is graded. There is a canonical way to include these A modules inside of A bimodals, and this is why you obtain the structure. So yeah, so we can say, oh, okay, but now what is the thing? How can I solve this problem? Because, and the idea, it's in some sense quite simple. Instead of take this, the things that you need really now, it's you can take here what is the eraser here? Yes, and an inclusion inside of the Dreamfield Center. If you have an algebra in the Dreamfield Center, now you have this half braiding, and this half braiding now allows you again to give an inclusion of A modules inside of A bimodals. And in fact, there is every equivariantization came from this construction. That's the point. So you obtain a go and back between this data. Yeah.
Okay.
And look, so that your initial category now doesn't. It is not necessary to be braided in order to do this construction.
Okay, but you sort of make your category of representations to be sort of generically be inside the sort of this half braidings, sort of the transparent object somehow.
Yes.
Okay. Okay. Thank you. Yeah, that's very subtle. The difference between A modules and A bimodules.
Yes.
Okay. Thank you. Thank you. And just finally, maybe, yeah. So okay, it was well, as far as I thought it was a very beautiful theorem where you could get your fusion category and then parameterize the fusion subcategories of the equivariantization with data from C and the action. But so suppose you have a braided category, and you have this situation here where you can de-equivariantize, and you know the fusion subcategories of the thing that it's going to be, that's later going to be your equivariantization. Can you get some information on all the fusion subcategories of the equivariantization of the braided category? I mean, can you make it sort of an inverse thing to? So the equivariantization seems to be sort of big, but somehow controlled. Can you control all the fusion subcategories?
I see your point. Yeah. I haven't think about that, because it's directly what you said. In general, if I have this big category because the dimension is bigger, I don't have a very good control over that. But in principle, it is not clear for me how the relation could be. I mean, because look, for example, in this case, that gives you only, in some sense, part of the fusion subcategories of C. It's only those that are invariant and satisfies a lot of conditions. So directly, it's not clear for me if it is possible to describe one in terms of the other. It's like a subset. It's a very particular subset. Yes.
Okay. Yeah. Thank you for the answer. And well, just finally, just a final question. Yeah, I'm sorry, I don't want to keep you here forever, but so I think it's a very beautiful theorem that you can describe the center of the G vector spaces through this equivariantization. But can you get like more constructions like this, where you get some type of fusion categories and some canonical actions on them, and then recover some classical constructions, other classical constructions as equivariantizations?
Well, let's say that the other one, it came from Hopf algebras, and one of the basic examples in the theory of Hopf algebras, and it's suppose that you have an Hopf algebra H, And inside of this algebra, you have the algebra of functions over your group as a Hofstad algebra.
Okay.
Even more, suppose that this is a central Hofstad algebra.
Okay.
So in this case, when you have that this is a central Hofstad algebras, this is a particular case of something that people call a normal Hofstad algebra. So you can construct a quotient. It doesn't matter too much what is the notation, but this is the quotient.
Okay.
And the point here is that the group G acts on the category representations of the quotient. Let me just denote the quotient by K in order to don't do this more complicated. So, and the category representations of H, it's tensor equivalent to the equivariantization of K by G. And there is a very, very interesting case of this, and it's when you take the quantum group where Q is a root of the unit, there is always the algebra of functions over the group. G is a semi-simple, or simple if you want, simple algebra, and this is the algebra of functions over the connected, simple connected Lie group associated. And here you have that this is, here I am saying something incorrect. This is, let's see here, maybe it's better to write down in this way. This is the quantum group, or the quantum group associated with this connected, simple connected group. This has a copy of the algebra of functions over G. And here you have that the quotient is the small quantum group associated with G. This is a finite dimensional Hopf algebra. So something that is quite interesting is that the category representation of this huge quantum group is the equivariantization of this affine group over the category representations of the small quantum group. And this is a beautiful result that, for example, Ettinghoff, Nitschich, Victor Ostrich, maybe I am forgetting some name, maybe Davido, they classify using, they classify tensor autoequivalence of the category representation of the big quantum group using these ideas.
Oh, wow. Okay.
Yeah. So this is another reason when the actions appears canonically. Look that here, your group is not really a finite group, but more or less that all things that I said can be translated to the using some algebraic geometry.
Okay. Yeah, that's another beautiful construction. Yeah. Yeah. Okay. Yeah. Thank you very much. That's all my questions. Thank you so much.
No, thank you.
I don't know if there's any other question by the audience. Okay, so thanks, Cesar, again. Thank you very much, Cesar. So I will